So today, we're going to dive into a technology that operates on a completely different level of reality. We're talking about quantum computing. Now, to really get it, you kind of have to forget the basic rules of the computers we use every single day and embrace the strange and seriously powerful logic of the universe itself. Let's just start with a big, mind-bending question. The phone or computer you're watching this on right now, it works with a pretty simple code: on or off, yes or no, 0 or 1. And yeah, it's powerful, but it's also limited. So what if a computer wasn't stuck with just two states? What if it could hold and explore every single possibility all at the same time? Well, that's not science fiction. That's the core idea behind a quantum computer.
But to really get a handle on where we're going, we need to be crystal clear about where we're starting. So let's do a super quick refresher on the classical computing that, powers our entire world right now.
Okay, so the heart of your computer, your phone, anything digital is the bit. And you can pretty much just think of it as a microscopic light switch. It can be off, which we call a 0, or it can be on, which we call a 1. That's it. Every single photo, every video, every single thing your computer does is built from billions and billions of these simple on or off switches.
A classical bit is definite. It's either a 0 or it's a 1. There's no in between. And this means when your computer has to solve a problem, it has to check each possibility one after the other in a line. Now, it does this incredibly fast, but for problems with millions or billions of variables, like, say, designing a new drug or modeling a global climate system, checking every single option one by one isn't just slow, it becomes physically impossible.
All right, now for the fun part. Let's take the leap into the quantum realm, where the fundamental rules of physics get weird, they get wonderful, and they get unbelievably powerful.
And this brings us to the hero of our story, the qubit. Now, unlike a regular bit, a qubit isn't forced to choose between being a 0 or a 1. Thanks to this amazing property called superposition, it can exist as a mix of both states at the exact same time. It's like a cloud of probability, and it's only when we look at it or measure it that it finally decides to be a definite 0 or 1.
This image just shows the fundamental difference perfectly. A classical bit, on the left, gives you just two choices, two positions. A qubit, though, on the right, well, it isn't a simple switch, it's an entire sphere of possibilities. Any point on that sphere represents a potential state, which means its ability to store and process information is just exponentially greater.
This model is called the Bloch sphere, and it's a great way to picture this. Think of the North Pole as 1 and the South Pole as 0. A classical bit can only ever be at one of those two poles. But a qubit can exist at any point on the entire surface of that sphere, representing this complex blend of both 0 and 1. And this isn't just some abstract idea. It's this very ability to hold all that nuanced, probabilistic information that unlocks all its power.
So, if superposition is the qubit's first superpower, its second one is even stranger. It's a phenomenon that Albert Einstein famously called spooky action at a distance, and its real name is entanglement.
This is entanglement. You can basically link two qubits so that their fates are completely intertwined. They become a single system. And get this, no matter how far apart they are, whether it's across a room or across the galaxy, if you measure one, you instantly know the state of its partner. So if you have an entangled pair and you measure one qubit and find out it's a 0, you know with 100% certainty that its partner is now a 1, instantly. This isn't just them talking to each other, it's like a deep, shared existence that lets these qubits coordinate in a way that classical bits could never even dream of. So, okay, we've got superposition, which lets a qubit be in multiple states at once. And we've got entanglement, which links qubits together. When you combine these two quantum superpowers, the result is nothing short of an explosion in computational power. And right here, this is where the game truly changes. With regular computers, if you add more bits, you get a little more power in a straight linear line. But with a quantum computer, every single qubit you add doubles its total processing capability. This isn't just slow and steady growth, this is exponential growth. And that is what sets quantum computing completely apart from everything that's come before. Let's just look at how this scaling works in practice, because this is wild. Two classical bits can hold one of 4 combinations. 2 qubits, because of superposition, can hold all 4 values at the same time. By the time you get to just 10 qubits, you're already juggling 1,024 simultaneous values. But what happens when you get to, say, 300 qubits?
Yeah, this is where our brains pretty much just short circuit. With just a few hundred entangled qubits, a quantum computer could process a number of possibilities that is literally larger than the number of atoms in the entire known universe. This isn't just a faster computer. It's a completely new paradigm of calculation.
Now, with that kind of power, you'd think quantum computers would be everywhere by now. So why isn't the device you're watching this on a quantum computer? Well, because building them is one of the greatest scientific and engineering challenges of our time.
But first, let's talk about the incredible promise. Imagine being able to perfectly simulate complex molecules, leading to brand new medicines and materials in a fraction of the time. Or solving logistical problems so complex, like optimizing global shipping routes in real time, that today's supercomputers can't even begin to touch them. This is the potential that's driving all this research, a tool to solve some of humanity's biggest, gnarliest challenges.
But you knew there had to be a catch, right? The very quantum properties that make these qubits so unbelievably powerful also make them incredibly fragile and just ridiculously difficult to control.
So the biggest enemy is this thing called decoherence. A qubit's quantum state is just so fragile. The slightest vibration, a stray magnetic field, even a tiny change in temperature can make it lose its superposition and just collapse. And that ruins the whole calculation. That's why you see these quantum computers in massive, shielded refrigerators cooled to temperatures colder than deep space. And on top of that, you can't even fix errors easily. Why? Because the very act of looking at a qubit to check its value forces it to collapse, destroying the very information you were trying to protect.
So I think the most crucial thing to take away from all this is that we shouldn't think of a quantum computer as just a super fast version of our laptop. It's a completely different kind of machine. It doesn't just use physics to work. It harnesses the deepest, strangest rules of quantum physics itself to actually compute.
We are right on the verge of a huge transition, moving from the classical binary logic of either this or that to the quantum logic of everything all at once. And this shift could unlock answers to questions we don't even know how to ask yet, which kind of leaves us with a final thought. If you had the power to explore every single possibility at the same time, what problem would you choose to solve?